In this video, we will use the work-energy theorem to solve the following problem. A pitcher in a baseball game can accelerate a pitch from rest to 95.5 miles per hour. During this acceleration, the ball travels a distance of 2.52 meters in a straight line. The baseball has a mass of 145 grams. We will consider the force the pitcher exerts on the ball to be constant and neglect any spin the ball might have. We're asked the following questions. What is the kinetic energy of the ball when the pitcher releases it? How much work does the pitcher do in throwing the ball? What force does the pitcher apply to the ball? What is the ball's acceleration? And then finally, how long is the ball in the pitcher's hand? Well, the first step in the problem-solving process is to figure out what the problem is telling us and to write out the data, paying attention to make sure that we are in the proper units. So taking a look at the problem, we realize that we are given the following data. We are told that the mass of the baseball is 145 grams. We can convert this into the units we need, kilograms, by using the conversion factor that there are 1,000 grams in a kilogram. This gives us a mass of 0.145 kilograms for the baseball. We are told that the ball starts from rest, so the initial velocity is going to be 0, and the final velocity is 95.5 miles per hour. Now, this is not the correct units. We need the velocity to be in meters per second, so we go through our conversion process. We realize that there are 1,609 meters in 1 mile, and that 1 hour contains 3,600 seconds. This results in a final velocity for the ball of 42.68 meters per second. And that's all the data we need to answer the first question, because we know that the kinetic energy final is going to be equal to 1/2 times the mass of the baseball times the final velocity squared. Well, that's just 1/2 times 0.145 times 42.68 squared. That gives us a final kinetic energy of 132 joules. Well, next we are asked how much work the pitcher must do to get the ball moving this fast. This is a situation where we use the work-energy theorem, which states that the work done by all the forces acting on an object is equal to the change in the object's kinetic energy. In other words, work equals 1/2 times the mass times the final velocity squared minus 1/2 times mass times the initial velocity squared. We know, as we've calculated above, that that final velocity is 132 joules, and we know that since the initial velocity is 0, the initial kinetic energy is 0, and so finding the work done is very easy. It's 132 joules. We are then asked what force does the pitcher apply to the ball. For that, we can utilize the definition of work. All right, work is the force we apply multiplied by the displacement multiplied by the cosine of the angle between the force and the displacement. And for this problem, the distance is going to be 2.52 meters. And the angle theta, in this case, is going to be 0 degrees, because the force is going to be exerted in the same direction as the ball's displacement. So this angle theta is going to be 0. And so we can say then that 132 joules equals our force multiplied by our displacement multiplied by the cosine of 0 degrees. Cosine of 0 is, of course, 1. And so that gives us that the force we apply to the ball is then equal to 132 joules divided by 2.52 meters, which equals 52.38 newtons. Now, since the problem has 3 significant figures, looking at our data here, we'll report that as 52.4 newtons of force. Again, we're considering this force to be constant. In reality, it probably isn't. It varies, but we're assuming it to be constant here, a value of 52.4 newtons. We're then asked, what is the ball's acceleration? There are actually 2 ways to go about figuring out the ball's acceleration. We can start one way with Newton's second law, force equals mass times acceleration. We've just calculated the force to be 52.38. The mass is 0.145, and so we can very simply calculate the acceleration of the baseball to be 361.2 meters per second squared. We can also utilize the kinematics equations, and we don't need then to calculate the force. We know that the final velocity is 42.68. The initial velocity is 0, and the displacement is 2.52. We square the final velocity, multiply the displacement by 2, and we arrive at a value for the acceleration of 361.5 meters per second squared. There's a slight difference between these 2 numbers, but we can account that by rounding error. The 2 values are actually quite close to each other. Notice that this method does not require us to first calculate the force, but it's a nice check assuring us that we did calculate the force properly. Finally, we are asked, how long is the ball in the pitcher's hand? And to calculate that, we can use the definition of acceleration itself. That acceleration is the change in velocity over time. Turning that equation around, we see that time is then the change in velocity over acceleration. And so the time that the ball is in the pitcher's hand is going to be 42.68 minus 0 divided by 361.2, and that gives us a time in the pitcher's hand of 0.118 seconds. So a little bit over 1/10 of a second for the ball to be in the pitcher's hand.